Hello, my name is Desmond Edagese, and I'm going to take us on the subject mathematics. We'll be looking at the theme numbers and numeration, and under numbers and numeration today we'll be looking at the topic indices. In our last class we looked at the first three laws of indices. Remember, we talked about the product of power law. Next we talked about the quotient of power law, and then we talked about the power of a power law. Well, in this class we're going to take the remaining three laws. I guess you are longing to know more about our remaining laws. Let's go into our class and then we'll see some more. We'll be looking in this class at the zero index law. Also, we'll look at the negative index law. And finally, we'll look at the fractional index law. Remember once again that there are conditions for all of these laws to be true. One of that basic condition is that our bases must be same. As we go into our class, we'll get to understand some more. The first law we'll be looking at today, which of course is the fourth law of indices, is our zero index law. It's a very interesting one. It basically states that for any quantity A raised to a power 0, our answer will always be 1. Let's see if we can prove this to be true. Assume you were given A raised to power 3 and you were asked to divide it by basically itself A raised to power 3 again. So we'll simply say A raised to power 3 divided by A raised to power 3. Of course, we know that to be 1. Anything divided by itself is 1. But by the second rule of indices, which we've learned so far, we take a different path, if you remember. This would be a subtraction of the powers 3 and 3. So we would have A raised to power 3 minus 3, which of course would give us A raised to power 0. What have we done here? We've simply solved this expression in two different ways, and of course our answers stand. So if we say A raised to power 3 divided by A raised to power 3 gives us 1, this is true. And we also said by our second rule of indices, 3 minus 3, which is our power, would give us A raised to power 0. And this is also true. That simply tells us that A raised to power 0, our answer here, is same as our answer here, which is 1. So from this conclusion, we can say that our zero index law is true. Let's take some examples. We'll see how this plays out. Okay, let's take a look at this example so we better understand our zero index law. We said any quantity raised to the power 0, be it a letter or a number, is equal to 1. This is pretty straightforward. Let's take a look at this other one. 6 times z raised to power 0. This quantity would give us 1. So our expression becomes 6 times 1, which would still give us 6. Let's also take a look at this expression here. A raised to power 9 divided by B raised to power 0. This would also give us A raised to power 9 divided by 1, which of course would still give us A raised to power 9. I guess we're following. Let's see this one. F raised to power 0, all in brackets, raised to power 8. Remember the power law of index that we looked at earlier. In this case, we would have F raised to power 0 times 8. of course, anything multiplied by 0 will give us 0 at the end of the day. So we would still have f raised to power 0, which of course we've seen to be equal to 1. The next law we'll be looking at is the negative index law. This law simply states that a quantity A raised to a negative power n is equal to 1 all over A raised to a positive power n. Our aim in carrying out this operation is basically to lose this negative sign. And as we see in our final answer, we have a positive sign here, but our number becomes inverted. So the negative index law again states that any quantity raised to a negative power becomes 1 over that quantity raised to a positive power. Let's see if we can prove if this is correct. Suppose we were asked to divide a raised to power 3 by a raised to power 7. Quickly you will notice that our numerator is smaller than the denominator. Let's see how this plays out. So a raised to power 3 divided by a raised to power 7 would be what? A raised to power 3 all over a raised to power 7. In expanding this, a raised to power 3 would give us a times a times a, while a raised to power 7 would give us a multiplied by itself 7 times over. Now if we crossed out like terms, we would have a cancels a cancels a. So in our numerator we'll have 1, and in our denominator we'll have how many a's left? 1, 2, 3, 4. So our answer becomes 1 all over a raised to power 4. Very interesting answer. Now let's try a different approach using the second rule of indices we've learned so far. Remember we said if we divide like bases, we simply subtract the powers. So this same expression here becomes a raised to power 3 minus 7, which of course is a negative answer. So we have a raised to power minus 4. So what have we done here? We've solved this expression in 2 different ways. And of course, the answer we got in this instance is true. And also the answer we got using our laws of indices is also true. So from logical conclusion, we could say a raised to power minus 4, which is our answer using this laws of indices approach, is same as 1 all over a raised to power 4, which is the answer we got using the long approach. So from this conclusion, we see that our negative index law is obviously true. As we take some more examples, we'll see how this works. Let's take a look at this other example. So imagine we had this to solve. Simplify 1 all over 7 raised to power minus 2. This would give us 1 all over 1 all over 7 raised to power 2. And this at the end of the day, it's simply saying 1 divided by 1 over 7 squared, which of course is same as 1 times 7 squared, which of course is 49. That's simple enough. If we're also asked to find something like this, a raised to power minus 2, b 3, this would be what? 1 all over, remember we are inverting a, but here our negative value has changed to positive. So we'll have 1 all over a raised to power 2 multiplied by b raised to power 3. Our b raised to power 3 remains itself because there is no negative annotation attached to it. So we'll simply leave our answer like this: b raised to power 3 over a raised to power 2. Let's look at some other examples. Remember what we said about the brackets? That for every content within the brackets, whatever operator we have outside of the brackets, that operator operates on every individual content within. Now what do we notice here? We have 3 types of content within our bracket. We have 3, we have A, and we have B. So we'll apply these to everything within. Alright, so we have A all over 3B. This is a fraction. If we were to invert this fraction, what would we have? It would simply be 1 all over A all over 3B, which would give us 3B all over A, all squared. So this situation gives us a general understanding that whenever you have a fraction and you have this negative power, what you are simply doing is inverting. So whatever was beneath as our denominator comes upward, and whatever was our numerator comes down. So instead of showing all of this, we could have simply said 3b all over a. That's the inversion that has taken place. Do we understand? So we'll have 3b over a all squared, which of course would be 3 squared times b squared all over a squared. And this would give us 9b squared all over a squared. That's our answer. Let's take a look again at another example. We're asked to find 3a all in brackets raised to the negative power 2. Once again, we said everything within the brackets is handled individually. We say this because most students will notice would say this is 3a raised to power minus 2, which would be 3 all over a raised to power 2. This is incorrect. So ensure that every individual object within our bracket is operated upon by the negative index. So this would be 3 raised to power minus 2 times a raised to power minus 2, which is equal to 1 all over 3 raised to power 2 and 1 all over a raised to power 2, which is simply 1 all over 9a squared. And that's our answer. The next law we'll be looking at is the fractional index law. The fractional index law states that any quantity a raised to a fractional power 1 over n gives us the nth root of our quantity a. So if we have a fractional power of 1 over 2, the root of our a here would be a square root. If we have a fractional power of 1 over 3, we would have a cube root of a. Let's see if this law is basically true. Let's take, for instance, 2 identical numbers multiplying themselves. Using 7 for an example, if 7 multiplies 7, of course our answer will be 49. We've learned that this could be written as 7 squared, meaning that 7 multiplied itself 2 times over. our base here tells us the number of times he multiplied the 7. So 7 squared is equal to 49. Now, imagine we wanted to get our 7 back. We'll simply take the square root of 7 squared. And of course, we'll do that for the other side. And we'll take the square root of 49 too. This would give us our 7 back. And we'll still have the root of 49. So we say 7 is equal to root 49. And of course, root 49 times root 49 again would give us 49. The root of a number multiplied by the root of that same number will give us the number. Let's write this concept out in letters. So instead of this, I could write a raised to power p multiplied by a raised to power p, and of course this could give us a. It simply means that our a raised to power p here represents root a. So a raised to power p represents root a. Now, we know from our earlier study that a raised to power 1 would also give us a. So, we could rewrite this statement as a raised to power 1 is equal to. Also remember, we learned that our powers here would add up because we have like bases and we are multiplying them. So this would be a raised to power p plus p, which would give us a raised to power 2p. We say a raised to power 1 is equals to a raised to power 2p. Therefore, if we cross out our like terms, we say 1 is equal to 2p. And of course, p will be 1 over 2. So we have our p as 1 over 2. It means that a raised to power p now could be written as a raised to power 1 over 2. But remember, we said that a raised to power p is a representative of square root of a. So our a raised to power half is square root of a. If we take a look at this expression here, it looks similar to what we have over here. A half, in this instance, n stands for 2, and of course our root a. Our root here being a square root. So in general, we say the fractional power 1 over n of any quantity a will give us the nth root of that quantity. And this is a proof of our law over here. It proves that our law is obviously correct. But quickly, there are instances where we have fractional powers in this manner. M over n. Our m here refers to our whole number power, while n represents our fractional power. So whenever you come across such situations, m represents a whole number power, while our n represents our fractional power. I'm sure if we take some examples, this will be very clear to you. Let's go into some examples and see. Now, let's take a look at this example. Just like what we said, you could have a combination of both your fractional index and then a power. If we were to break this down, this would simply be 16 raised to our fractional index all of that raised to the power 3. So you could have a combination of a fractional index and a power. Remember we said when you have fractional index, it is the nth root of whatever quantity you were asked to find. So how would we go about solving this? This would give us the 4th root of 16 all raised to the power 3. And this, of course, is what? 2. It tells us that 2 times 2 times 2 times 2 would give us 16. So our 4th root of 16 is 2. But remember, we still have a power out there in the bracket. So this gives us 2 raised to the power 3. And this, of course, gives us 8. Alright, a quick one. When you have a situation where you have a combination of fractional powers and a power, it is better that you solve the fractional part first before you raise it to a different power. But also, we also said it could be either way. We said earlier that the multiplication for such cases are commutative. This simply means that this same statement could be written as 16 raised to power 3, and of course our fractional power outside of the bracket. So you can write it this way or this way. It's commutative. But for simpler emphasis, it is better that you solve the fractional part first and then you raise it to a power. I hope you understand. Let's go forward and see another example. If you are given, for instance, this again is a combination of fractional powers and a power. This would be, again like we said, let's break this down. We would have 8 raised to our fractional power, all raised to power 2. It is better you follow this order. This, of course, gives us the 3rd root, which we call the cube root of 8, all raised to the power 2. And of course, this gives us 2 raised to power 2, which of course gives us 4. Yet again, let's look at this example. We have 16 all over 81. Again, as we said, let's break this down. We would have 16 all over 81 fractional power all raised to power 3. So let's solve this within the bracket first, and then we apply our power to 3. This would give us 16 over 81 4th root all raised to power 3. This, of course, will give us 4th root of 16 will give us 2, and the 4th root of 81 would give us 3. So this is this, and of course we would have 2 raised to the power 3 is 8, 3 raised to the power 3 is 27. And that's our answer. Let's also quickly look at this. We would have in this instance 27 raised to our fractional power, all raised to our power 5. If we solve this, it would give us the 3rd root, which is known as the cube root of 27, all raised to the power 5. The cube root of 27 would give us 3, and this would be raised to power 5. This, of course, is 243. I hope we're following. Let's take a recap of what we've learned in our class so far. We've looked at the remaining 3 laws of indices. We looked at the zero index law, which states that a quantity raised to power 0 will give us 1. Next, we looked at the negative index law, which states that any quantity raised to a negative power would be 1 over that quantity raised to the positive power n, for instance. Finally, we looked at the fractional index, and we said any quantity raised to a fractional power 1 over n would give us the nth root of that quantity. And we said in some instances, a fractional power may have a number as a numerator over here. That number is our power in whole number, while the n represents a fractional power. With all of these laws, I'm sure you've come to master the laws of indices. Well, guess what? It was a pleasure for me to take you in this class, as I look forward to seeing you in our next class, where we'll be carrying out exercises for all that we've learned so far, to see how much we can remember. Till we meet again next time, my name is Desmond. Bye for now.